All right, everyone. Well, welcome back. Hope you went and got yourself a fresh mead. And we're ready for part two of our MeadCon virtual night, and that is a malolactic fermentation talk by Tom Repas. Introducing Tom is kind of weird. The whole like needs no introduction thing is like probably overdone, but for him it feels weird. It's almost impossible to me that you would be on this call and not know who Tom was. But in case you don't, he's a fourth generation beekeeper. um in high school he kept bees and then sold the honey for money when people like me just had to sell drugs. um but and is you know Any list of the best home mead makers in the world would include Tom on it. He's won more medals than probably anybody could count. Um, and was is famous for really including great traditionals from his own honey. Uses and as well as big meads and meads that burst with flavor of really all kinds, including a mushroom mead that I'm told was really something at one point. Um, and in addition, Tom is a man of science, and really one of the greatest minds I think we are lucky enough to have in the mead industry. There is basically no time he talks where we all don't learn something. So I know we're all looking forward to it tonight. So without further ado, I will give our thank you shout outs again to Tim Lieber and Dan at Spacetime Meadworks, and then turn things over to Tom.
Well, thank you, Greg. I'm glad we're able to pull this off. I'm kind of bummed. I made some samples for us to share in March, but of course, with the pandemic, those samples are just sitting there waiting. So this talk,
Hey everyone, give us a quick second. It looks like Tom might have just dropped off. We'll try to get this figured out. Just give us one quick second while we check this out. Thanks.
back. Let me see if I can share the screen again. Okay. Now, here I am.
It wouldn't be any type of MeadCon if we didn't have some type of technical
Okay.
issue.
I was like, start talking, and I'm like, even the computer doesn't want to listen to me. Okay. I think I'm back now. Where's my little... Well, you guys can see it now, and you can hear me. It looks like...
You'll have to share your screen again, possibly.
Okay. Come on. Come on. now it's just sort of. Here we are. Share screen. There.
All good to go.
Okay. Here we are. So anyway, you know, a lot of us as homebrewers, we think about fermentation from the yeast standpoint, of course, making alcohol, and we don't think that much about bacteria unless they're causing problems. You know, you have a unintentional infection or a wild fermentation, and sometimes we dabble in that. Those of us with a beer background, we do that on purpose. But much of the time when you have bacteria in your mead, it's something that's unwanted. And it wasn't until Emil Pinot and some others started recognizing that malolactic fermentation in wine is something that can be very useful. And so in this presentation, I'm going to talk about what malolactic fermentation is. And again, I'm not really talking about wild fermented or sour meads. That's a whole nother presentation in and of itself. So I'm really talking about malolactic fermentation from as the standpoint as a winemaker, or to some extent some cider makers may use. I'm going to talk about why use it, what are the beneficial and also potential negative effects, how to optimize it or prevent it if you don't want it, and then how to monitor it. And so for centuries, winemakers would observe another fermentation beginning, and they called it a quote unquote secondary fermentation. Usually it happened in the spring after the harvest. So after the yeast fermentation in the fall was completed, the wine was put into barrels and they sat there. And then on the arrival of spring, they started seeing some activity, some CO2 production, and the wine that was clear became cloudy. And so that was their quote unquote second fermentation. And at the time, they didn't know that it was a bacteria. They didn't even know about yeast or microbes. And it was always thought, at least early on, it was thought to be something that was undesirable. Some of the early enologists recommended racking and sulfiting to try to keep the wine clear, to keep it from developing the second fermentation. Louis Pasteur isolated bacteria from wine, and he thought that all bacteria were something that shouldn't be there. And then finally, Hermann Müller-Thurgau recognized that perhaps this activity from the bacteria is reducing some of the acid in the wine. And it wasn't until Jean-Louis Gaillon started recognizing that bacteria in wine can actually be beneficial. And this was taken further by his student, Emile Pinot, to be something that is considered in some wines to be essential for them to really meet the character from that style of wine. And finally, we started having commercial malolactic bacterial cultures available starting in the 1980s. So there's several species of lactic acid bacteria, and they don't only metabolize acid. The name malolactic fermentation is somewhat of a misnomer because they do much more than convert malic acid into lactic acid. And it's actually not technically even a fermentation at all. It's a decarboxylation of malic acid into lactic acid. But since we call it malolactic fermentation, and that's what we call it, that's kind of what we use, even though it's not exactly accurate. And so they can metabolize citric acid, and that's how we get the diacetyl, the buttery notes that you might get from, say, a Chardonnay. But there can be some negatives too: increased volatile acidity, biogenic amines, the dreaded geranium taint. That's the sample that I had made to share at MeadCon. My one I was most proud of was the one that had the geranium taint because it was so awful. You'll never forget it. And I honestly think it's worse than geranium leaves because geranium leaves aren't that bad. I don't want them in my mead. But that's the one that maybe I'll have to bring to a future MeadCon just to share so you guys can see what it is. So in a very simplistic way, we think of malolactic bacteria converting the malic acid into lactic acid and CO2. And it can be beneficial if you have a mead or that has malolactic acid in it. So that would be piments, sizers, certain types of melomel. You can decrease the total acidity by 1 to 3 grams per liter and increase the pH slightly. So you can take something that's almost overly tart and you can kind of smooth it out and take some of that acid away. Now, malic acid exists as 2 stereoisomers, dextromalic acid and levomalic acid. And only levomalic acid exists in nature, and that's what the malolactic bacteria will metabolize. The reason why this is important is if you get a acid blend, or if you are buying malic acid, just commercially to add to your mead, and you added too much, if you decided to use malolactic bacteria to reduce that, that wouldn't work so well because it's actually not pure levomalic acid. It's usually a blend of dextro and levomalic acid. And so that's why you really, if you over added malic acid from a commercial acid blend, probably MLF is not the best way to manage that. You may have to do something else, maybe perhaps back sweeten to try to reduce the perception of the acidity. Now, there's a lot of fruits that have malic acid in them. We think about grapes, of course, because that's where malolactic fermentation is used commonly. But other fruits have it too. Apple, so it can be useful in cisers. Some fruits have it, but they're relatively low acid, like peach, for example, or watermelon. Even though it is very high in malic acid, it's not a high acid fruit. So, if you can make a malolactic fermented watermelon mead that tastes good, go for it. I'd love to try it, but I can't imagine how it would be anything that would be very enjoyable. So many things can affect the malic acid levels in fruit. And a lot of us know this intuitively, and that's why it's so hard, when somebody says, "What's your recipe? What's your recipe?" And I can't tell them that because every variety of fruit I use is different. Even within the same variety, it can be different year to year, depending on if it was a wet year or a dry year. Even within the same orchard, the fruit can be different, or within the same vineyard. You can have grapes that were grown on the sunny side of the hill can be totally different than the ones that were grown in the same year, same vineyard on the north side of the hill. And other factors can affect the malic acid concentration as well, such as potassium. Cooler temperatures increase acidity, so a lot of cold climate grapes are high acid, and so malolactic acid can be helpful to reduce that in wines and piments. Now, before I go on more about the malolactic bacteria, there are yeasts that will metabolize malic acid. It's not a malolactic fermentation the way the bacteria do, because they're not converting it into lactic acid, of course. They're basically metabolizing it into ethanol. But one way, if you have a high malic acid mead of some kind that you want to reduce the malic acid a little bit without using a malolactic bacteria, you can use some of these yeasts, and that can be helpful. And there's some non-Saccharomyces species of yeasts that can do it too, but they're really not available commercially. If you're doing research or whatnot, you can probably find a culture of that, but they're not commonly available, like the Schizosaccharomyces pombe, for example. So different species of malolactic bacteria. Primarily, the one that we think about is Enococcus. It was formerly known as Leuconostoc. Lactobacillus and Pediococcus, those are also malolactic bacteria, but they tend not to be found or commonly used in the commercial MLF cultures, unless you're using like a one that's been made for beer, perhaps for souring. But again, we're not really going to be talking about that. So really, Enococcus is primarily the one that is the species, the genus of bacteria that we're using when we're purchasing a commercial MLF culture. So, and to clarify some of the terms, there's heterofermentative bacteria and homofermentative bacteria. So homofermentative bacteria, they only convert malic acid into lactic acid and carbon dioxide, whereas the heterofermenters, they do the lactic acid, of course, and CO2, but then they do other, and the other can be a good thing or it might be a bad thing. It depends on what you want. If you want a little bit of diacetyl, you might pick a strain that is a heterofermenter that will produce diacetyl. But heterofermenting can be bad if the other is actually volatile acidity. If it's acetic acid and ethyl acetate, that's an other that you probably don't want. And so that when we talk about homofermenters and heterofermenters, it really depends. Do they have anything other than lactic acid and CO2? And here's some of the examples of some, whether they're heterofermenters or homofermenters. So the way that it generally works is the yeasts ferment early. There's an alcoholic fermentation. The lactobacillus can begin fermenting early. If it's an infection, that's probably something you don't want. So that's maybe why you might sulfite your must, let's say if you're making a wine or a piment, whereas the Enococcus may be stunned a little bit by that, but then will start fermenting later on in the fermentation process. And then if you did not sulfite properly, the Acetobacter can start making vinegar later on when you're aging your mead or wine. And in general, what happens is the malate starts dropping first, and the lactate is increasing. And then if you have a heterofermenter that's doing something that you don't want, that's when you can get some more volatile acidity later on, which is a reason to perhaps choose a selected strain and pitch that rather than sort of crossing your fingers and letting nature take its course and hoping for the best. So reasons to perform malolactic fermentation. This is not something that we think about doing in, say, a traditional mead, although I know people who have done it. I've done it accidentally. It wasn't so good, but when you're thinking about in a mead or a fruit-based mead, the reasons to consider doing it, well, number one, it is used to lower acidity and raise pH. So if you have one that's just overly tart and puckery and you want to cut back and smooth out that acidity, malolactic fermentation can be used for that. But this fermentation, this bacterial activity is for much more than only lowering acidity. It can help reduce the chances of a future unwanted fermentation, like in the bottle. I've had that happen too, where there was a wild malolactic bacteria got in a bottle, and it was kind of unfortunate. And this was before I knew how to sulfate properly and stabilize. And it was a dry piment, but it was kind of unfortunate. It was a beautiful thing when it went in the bottle. It aged for like 6 months or a year in the bottle. It was really good, and then some of those bottles were bad. So there was some of the bottles were really great, and some of them were bad. And it was because some of them apparently had some some wild bacteria that had gotten in there. Since I've learned how to stabilize better, so I haven't had that happen so much. But if you did a MLF fermentation on purpose with the bacteria you chose, you're less likely to have that happen. And then finally, there could be beneficial changes in aroma and flavor, even beyond anything that it's doing to the acidity. And it's hard to describe, but there's a complexity you can get from malolactic fermentation, and it's not not just diacetyl. It's not just the common things that we often think about. But overall, the effects can be either positive or negative, and it really depends. Most of you who know me, it depends. So some of the effects, some of the potential positives, I already mentioned. It can reduce acidity. If you want that butteriness, the diacetyl, that can be a pleasant thing. It can also improve the flavor. It can make a piment or sizer or wine seem less vegetal. It can make it seem smoother, round out the mouthfeel, and lower astringency and bitterness. Some of the potential negatives, though, is you can have increased volatile acidity. Again, more likely with a wild MLF than one that's a commercial strain. You might not want diacetyl. So if you have too much diacetyl, maybe you don't want that, and that could be a negative. So it could be a positive if you want it, or it could be a negative if you don't. Sometimes it can change the pH by too much, which can change the color a little bit. So instead of being like the ruby red, it might be more of a rust color. There's a chance for ethyl carbamate, which is a potential carcinogen. Biogenic amines, those are what often give people the quote red wine headache, or so we think, more so than sulfites. Geranium tate, and then other potential off aromas and flavors. So in styles where you have high acidity and excessive tartness from the malic acid, it can lower that acidity by converting the malic acid into lactic acid. And lactic acid is less sour by perception than malic acid, all things being equal. So that's why MLF fermentation will make it seem a little bit less tart. But not all styles benefit from that. So something that doesn't have much malic acid, they don't have anything to work on, so they may work on something else, and maybe it'll produce something that you don't want. Some styles you want that bright, crisp, high acid, fruit forward, style, and so you don't want to really impinge upon that by adding malolactic bacteria. Those which are already low in acid and high pH at baseline, you don't want to lower that anymore. So that's another style that you probably wouldn't be using that. So what about gluconic acid? That's the main acid in honey. And so if you have a traditional mead, that's going to be the main acid that they're going to work on. And these bacteria work on other things too. They'll work on sugar and some of these other things. So they're not only, just like the yeast. The yeast needs other nutrients and things. It's not just going to eat the sugar. But the gluconic acid, it will be converted to lactic acid, and also to acetate, which is acetic acid and ethyl acetate. So again, this might be something that's unwanted if it increases volatile acidity. That said, I know people who've done this and they've really liked what the outcome was. I think this is an area of mead making that really deserves more investigation. I mean, I wish I had access to like a university level lab with like gas chromatography, and I could really see what it's doing, not just really in the flavor, but like even in the aromatic chemistry. You know, what kind of esters are some of these strains doing? There might be some malolactic strains that may be okay or really good in a traditional mead, whereas other ones they would be like, don't go there. But there's not really been much studied or done with this in traditionals, and it's not something that I would do, like, you know, without having done a bunch of experimentation with smaller batches to see, you know, is it doing something positive, negative, indifferent? But, you know, again, this is sort of a representation of all the different things that malolactic fermentation potentially can do. Here on the left, you know, it's just converting malic acid to lactic acid. And there's many that's all they really think of. But then you have all these other things that it can happen. Some of them good, some of them not so good. So it's very complex and can do many things beyond simply lowering the acidity. So let's talk about diacetyl. Again, that's the compound that gives that buttery butterscotch type of character that we often get. A great example is a buttery Chardonnay, which you know, some folks love it, some people don't. But if you have a Chardonnay that did not have malolactic fermentation, it's like they're almost a completely different wine, not even a completely different wine, but you know, if you didn't know, they'd almost seem like a totally different grape was used to make that wine. So the diacetyl can increase the aroma and complexity, but it can also be undesirable and overpowering. So like with a lot of things, balance, you know, if you want that and it gives you what you were looking for, that can be a great thing, or it can be too much. And then, you know, then it kind of degrades from what that product could have been. But the metabolism of citric acid, besides being converted into diacetyl, can also become acetic acid, vinegar. That's definitely an unwanted thing. This is more likely with the non-selected strains. So that's why we tend to avoid using citric acid additions in a mead that you're going to be using for malolactic fermentation later. They had thought that if you co-inoculated, and what that means is if you added the bacteria culture and the yeast culture at the same time, because of competition and some of the interaction between the yeast and the bacteria, you may have a high risk of this happening, but that's actually being debated now. So not everybody believes that. And then there's the esters that can happen with this. They're volatile compounds, of course, and some of them are already there. They're already from the fruit or the honey that we use. But the malolactic bacteria can either increase or decrease some of these levels of esters. This is another area that I think could really be, a lot of research could be done in mead and malolactic fermentation, and not so much with the very, you know, closely wine-based, you know, types of mead, because we're fairly familiar with that. But in mead that's not, you know, wine like, that's not a pyment, you know, in a traditional mead, it would be very interesting to see what is happening outside of the acid change, outside of the acid reduction, in regards to some of these aromatic compounds, you know, positive or negative. So acetaldehyde, you know, it's a compound that can happen. When it's too high, it's considered an oxidative flaw. In some meads, you know, like some of the delightful aged meads, you know, the Polish meads, you want that because it gives it the sort of that sherry-like note. But if you're trying to do something that is more of a, you know, that's not that's, you know, pyment or a sizer or a melomel, you know, acetaldehyde can be distracting. And so some malolactic bacteria can actually metabolize the acetaldehyde and reduce it, which can be a beneficial thing. Because if you have too much of it and, you know, and you want to get rid of it, there's other ways. For example, potassium caseinate, that's a fining agent. But malolactic bacteria themselves can actually metabolize and lower the amount of acetaldehyde that is there. One problem, though, is because sulfites will bind to acetaldehyde. That's one of the ways you can manage acetaldehyde. You add sulfite, it binds to the free oxygen, it binds to the acetaldehyde. But when the malolactic bacteria metabolize the acetaldehyde, it can raise actually the free sulfites within your pyment or within your mead, and that can actually interfere with the malolactic fermentation because the malolactic bacteria are relatively sensitive to sulfites as compared to yeast. So this is a situation where if you had added a lot of sulfites before, now you have acetaldehyde because you didn't prevent oxidation, and you're trying to do a malolactic fermentation, it might not work out so well simply because of the acetaldehyde bound sulfites being released that weren't there previously. This is just an example of several different strains of malolactic bacteria and what they do with acetaldehyde, showing that some of them can drop it, rather quickly, and some not so quickly and some not at all. But by doing that, by lowering the acetaldehyde, you may not need to use as many sulfites later to manage this. Now, biogenic amines. A lot of folks can have a red wine headache, which, I mean, you can get from drinking too much red wine, obviously, or alcohol. But some folks can get this from, not very much. Even a small amount. Just even a glass, and people can get a headache. And some people, say, oh, it's sulfites. Well, actually, red wine has less sulfites than white wine, so that's not really the cause. But the thought is it may be these biogenic amines, so histamine, tyramine, and some of these others. And some of the malolactic bacteria can actually produce this, especially the wild, the non-selected strains. And some of them can also produce, some of these actually have really unpleasant smells. I mean, just the name, putrescine, cadaverine. I mean, it smells putrid or like rotten meat. I mean, that's not a good thing. And again, these are from more the wild lactobacillus rather than the strains that are selected to not do this. And here's just an example of some of the differences in the different strains. In this study, they didn't actually identify what strain each of these were, but these were 3 commercial strains and then a spontaneous one. Ethyl carbamate, that's a potential carcinogen that is in many fermented foods and beverages, including alcoholic beverages. And basically, it's a reaction of the ethanol with a precursor, typically citrulline or urea back in the day when they were using urea as a nitrogen source. But certain strains of malolactic bacteria can create ethyl carbamate from arginine or citrulline, and adding too much excess nutrient additions beyond what the yeast can actually use in the initial alcoholic fermentation can promote that. So some of the ways you can prevent that from happening is either to not do a malolactic fermentation at all, to inhibit it with sulfites after it's done so that it's not going to keep working and producing some of this other stuff from, say, some of the nutrients that might have been left over from your initial yeast fermentation. And then some of the selected strains you buy also are supposedly lower producers of ethyl carbamate as compared to non-selected strains of bacteria. The dreaded geranium taint. For one, it's actually not geraniol. I hear a lot of people say, oh, it's from geraniol. That's actually a different substance. It's actually from 2-ethoxyhexathreefive-diene. My own personal thought is this is actually a lot worse than a geranium. A geranium plant is not, the leaves are kind of stinky, but they're not as bad as this. I mean, it's undrinkable. I can't describe it. Maybe wet, moldy, musty geranium leaves or something like that. And so I had made a batch where I spiked it with sorbate on purpose, and then I added a malolactic bacteria, and it's very distinctive. And swinging and stabilizing with sorbate, obviously you do not want malolactic fermentation to happen, and so you're going to need to make sure you sulfite it. And if you're doing a malolactic fermentation, for example, in another batch, you might not want to use the same wine thief to take samples out. I know because I've been there. So you don't want to do any cross contamination or anything like that. There's other off flavors too. This is more from the lactobacillus and pediococcus. Some of these barnyard flavors, which we usually think about with like Brettanomyces, which is a yeast, but it can actually happen from some of these bacteria also. But with the selected strains, it's much less likely. So, I don't have anything against wild bacteria. I've done wild fermentations over the years, and I think it's kind of fun. I mean, I bake sourdough bread, and that's a complete wild fermentation, but it's bread. But when I spend a lot of money on honey, or even if it's honey that I produce myself, it's kind of sad that, you kind of let nature take its course, and now you have a batch that you kind of have to dump out. So the same way that I like to use selected strains of yeast, I also use selected strains of malolactic bacteria. Again, not to say that it can't be done. And if you're in maybe a winemaking region where there's a lot of these microbes are in the air and they're in the dust and they're just settling, on the fruit you're using, you might probably be able to get away with it. But out here in the middle of nowhere in South Dakota, we're not having a lot of those good microbes floating around, although they are very good for making sourdough bread. I have to say that. Some of the other potential issues, which I've never actually experienced myself, but some of these, again, these are the wild bacteria. They can cause acrolein, which is a bitterness. When they metabolize glycerol, there can be a ropiness, so it causes these polysaccharides to form. So it's like an oiliness and increased viscosity. And there's certain wild lactobacillus that can degrade tartaric acid, which usually is microbe resistant. Nothing really works on that, but there are certain lactobacillus species which actually can metabolize that, and it can lower the acidity to where it's like there's very little acidity at all left. But it's more likely with the wild strains. You just don't know what you're getting. So optimizing malolactic fermentation. Well, for one, we should choose a yeast strain that's compatible with the bacteria. There's the big question, timing of the inoculation. Should you inoculate at the time you have the yeast fermenting, or wait until that's done? Should you use selected versus wild malolactic bacteria? Should you use complex nutrients? Do you want diacetyl or do you not want diacetyl? And then try to avoid factors that negatively affect the fermentation that can make it sluggish or stuck or just not happen. So here's a chart. This is modified from Scott Labs, and basically the ones here on the left, a lot of these are pretty popular yeasts that we all use, and these are ones that are more favorable to malolactic as compared to the ones that are on the left, or I'm sorry, on the right, that are less good to be, less compatible. Not to say that you can't do it, but if you're planning on doing a malolactic fermentation, you might want to choose one of these yeasts that play well with it. So there are lactic acid bacteria everywhere. I mean, to make a sourdough, you just set out flour and water, and the yeast will get in there, and the lactic acid eventually will grow, and that's got lactic acid in it. And so it does occur on fruit. But the problem is you might get some of these things you don't want. You might get some spoilage bacteria. You might get biogenic amines. It might be sluggish. The quality might not be as good. It might be less predictable. And so by using a commercial culture with Enococcus eni, you're less likely to have that happen. So the other big question, or sometimes even debate, is, should you pitch the bacterial culture at the time of the yeast pitch, co-inoculation, or should you wait until the yeast fermentation has been completed? So it's co-inoculation versus sequential inoculation. And the benefits of the co-inoculation, number one, there's more nutrients available. The yeast haven't worked on all of them, so there's more basically food for the yeast and the bacteria. There's less alcohol present, so it's less likely to suppress the bacteria. It's thought to have lower diacetyl production. The malolactic fermentation completes more rapidly, but there's a possibility of increased volatile acidity, although that's been debated. Some of the disadvantages, the yeast and the bacteria may compete, so you might get a stuck yeast fermentation. Actually, one of the things that can be done is if you have malolactic bacteria and yeast that you're fermenting together, or maybe you don't know but you suspect it could be, throwing in lysozyme in there can sometimes help the yeast fermentation restart. This is especially if you're using wild, or if you're using fruit or grapes that may have had bacteria that are already on them, and you didn't sulfite as much. Sometimes using the lysozyme, which actually will inhibit bacterial fermentation. And then the heterofermenters sometimes can produce unwanted byproducts. But again, it's more likely with a wild MLF that you don't know, really know what you're going to be getting. So waiting until after the yeast fermentation has been completed, sequential is more common. And honestly, that's what I prefer to do myself. So there's a lower risk of the yeast and the bacteria competing. There's a low risk of yeast fermentation, obviously, because you fermented with the yeast first, and then pitched the bacteria. There's a low risk of elevated volatile acidity, and you can get higher diacetyl production if that's what you want. Disadvantages, because yeast fermentation has happened already, there may be some factors present that may make it harder for the bacteria to work. So there can be sulfite present. Even if you did not add any, some yeasts will produce sulfites on their own. The pH can be lower. There's alcohol present, which inhibits all microbes, including not just yeast, but also bacteria and some other inhibitory factors. And there might not be as many nutrients available for the bacteria. And the other problem is, without there being bacteria early on, there might be a wild bacterial infection occur that you didn't want. Now, of course, that can be managed by sulfiting your must, especially if you're using fruit or grapes and you're making something like a piment. That's why you would sulfite the must, because the yeast is relatively more sulfite tolerant as compared to bacteria. And then by the time the fermentation is over from the yeast, then the sulfite levels are going to be a lot lower, and you can put in your bacterial culture at that point. So these bacteria need more than just acid. Like any other living thing, they need vitamins and nutrients, amino acids. Unlike yeast, they can't use inorganic nitrogen such as DAP. Fine lees can help provide nutrition, such as when you're aging surlees. So if I'm planning on doing a malolactic fermentation, I don't wait until the mead has aged and is crystal clear and there's no lees at all. I might rack it off of the gross lees, and then it's still going to be a little bit hazy. So I know there's still some stuff in there for them, and then you can have them in this batch with the fine lees, which and if you stirring that up too, so the bacteria have access to. Commercial nutrients, I have to admit, I was malolactic fermenting even before any of these proprietary nutrients were available. So you can definitely do it without adding these nutrients. They're not as required quite as much as, say, we need to use the nutrients for a traditional mead for the yeast. But they are useful. There is Acta ML, which is kind of like, I think of it like Go Firm, and then the Optimalo Plus, I kind of think of that like the Firm K. I've done it with and without, and I think they ferment faster if you use these nutrients. But if you don't have them, you can do a malolactic fermentation without, and it's not like you get a lot of bad off flavors or aromas like you might if you had a nutrient stressed yeast fermentation. And I tend to ferment, do malolactic in an oak barrel too. So I think there's stuff in there for them also. This is just showing different strains of bacteria and how it did ferment faster with the proprietary nutrient addition. They'd still fermented. I mean, they still were working on the malolic acid. It's taking a lot longer. Here's another one looking at the other addition. So much faster if you use the ingredient, where the other ones are still working, but they're just going a bit slower. So if you want that butteriness, again, some people don't like it very much and some people love it. I think it just really depends on what you're trying to aim for. But there are strains that that are high diacetyl producers. So if you're wanting that, then you would choose one of those. And then there's strains that are low diacetyl producers, which if you only want to reduce the malic acid but not put anything in there that's going to distract from your end product, then you probably might want to use one of those that are low diacetyl producers. There are things that you can do as you're doing your fermentation that can increase diacetyl. So I already said, choose a high producer. So decrease contact time with the lees, rack off the gross lees before pitching the culture. Add it after the yeast fermentation has been done, because the yeast will degrade diacetyl as it's being produced. If you have a slower fermentation, you'll have more diacetyl. So lower pH, low temperature, low inoculation rates. Basically, you're kind of stressing that a little bit, the bacteria a little bit. So you'll have higher diacetyl. Stirring can help do that. But if you have diacetyl, just be aware, if you add sulfites, they'll make them kind of magically seem to disappear. But then as the sulfite reduced, then the diacetyl will sort of reappear. It's due to binding. Now, if you don't want diacetyl, you choose a low producer. You'd have more time with the lees in active yeast. You might add it at the same time as the yeast alcoholic fermentation, again, because the yeast will degrade diacetyl. The faster you do the malolactic fermentation, the lower diacetyl. So high pH, higher temperature, higher inoculation rates tend to produce lower diacetyl. And then you might have more reductive conditions, so lower oxygen, not a lot of stirring, not a lot of racking. And then adding sulfite when there's diacetyl present, then that'll stop the MLF and you won't have more increase in it. And the other, so when you're trying to pull one of these off, it's important to try to have conditions that are favorable to the bacteria. And the selected strains are much more tough, for sulfites and things like that as compared to the wild cultures. But you really want to aim for one that's not too high in alcohol. So, less than 13% if possible, not too acidic. And that sounds kind of like it's counterintuitive because it's like, well, I'm using this to lower the acid, so it might have a lower pH. And so you can use it with a lower pH. Just realize it might be a little bit harder for the bacteria to pull off, especially if it's a low pH and it has all these other things that are harder. So it's like a low temperature and a higher sulfite and higher alcohol, that might be hard for those bacteria to pull off. But if you have a lowish pH, but everything else is really favorable, then the bacteria can pull it off. And because the bacteria, I already mentioned this, because they metabolize acetaldehyde, the sulfites bind to acetaldehyde and other things, and it can release sulfite that wasn't there, and it can inhibit the fermentation. So the total sulfites should be low. The total. So most of us as home brewers, we think about free SO2. We also think about molecular SO2. We don't think about total that much, because we don't have to test for it. If you're a commercial winery or meadery, there are regulations and you have to keep the total under a certain amount. And so why that is important is if you sulfited before and some of it was bound and now the free sulfite is low, it's less than 8, you might think, hey, I'm good. But if you had added a lot of sulfite and it bound and it's sitting there, it may become unbound once the bacteria start working and actually inhibit the fermentation. And you might not have expected that because your free SO2 was not that high. So just be aware, if you had done some additions already, they might be sitting there bound and you may not be measuring the free SO2, and it still can inhibit the fermentation. Sometimes we don't want a malolactic fermentation. For example, in those bottles I mentioned, where some of them were really great and some of them had a wild malolactic fermentation, and the piment was, was really sad. It was kind of like, oh, we'll open the bottle, it might be good, or we'll have to pour it out. And, it was kind of sad that that happened. Definitely a bad thing if you're commercial, of course, to have, some of your bottles turn out that way. So we don't want it to happen after bottling, obviously. Some styles benefit from being crisp and high acid. I think the Sizer is a really good example for that. Maybe you don't want it to be that acidic, and maybe you want it to be smoother, and that's fine. But some Sizers, you want that appleiness and you want that acidity, and so you don't want a malolactic fermentation. It really depends on what you're trying to do. And then, of course, if there's sorbate already in that, you definitely don't want that to happen. So some of the ways to prevent it from happening in the bottle is, well, do the malolactic fermentation before, and then they're not going to become active after bottling, unlike yeast, because you're not adding sugar and things like that. Maintain adequate molecular sulfites. Low pHs tend to discourage MLF, but again, we might use it because of high acidity. There's an enzyme called lysozyme, and then there's some other methods which I'm mentioning here, but these are probably really not available. Well, sterile filtration is, but the other ones are really not available unless you're like a really large a winery. But I'm mentioning just out of interest, and so that you're aware of them, so that if you hear of them, you're familiar with them. So some microbes are more sensitive to sulfites than others. Saccharomyces is relatively tolerant, which is why we use that for our alcoholic fermentation. But the bacteria themselves tend to be more sensitive. And the molecular sulfite, the cutoff is around 0.8 milligrams per liter or higher. And, I went over this in great detail in my sulfite talk I gave a few years ago. But the molecular sulfite, of course, is dependent on the acidity. So, and the free SO2. So whatever the pH is, there are calculators online where you can see what the free SO2 is and see what the pH is, and then it'll calculate and tell you what your molecular sulfites are. But basically, to inhibit these type of fermentations from happening, you can just make sure to have enough sulfites present. lysozyme. So basically, this enzyme will degrade the cell wall of gram-positive bacteria. So Enococcus and Lactobacillus, they don't do anything for gram-negative bacteria, so they won't prevent, vinegar from happening with Acetobacter, and they certainly don't do anything with yeast like Brettanomyces, obviously. And one of the benefits of using lysozyme is you can, if you don't want the malolactic fermentation, is you can also prevent the biogenic amines that cause the quote red wine headache unquote. It can last fairly long in whites, but because reds have tannins, they interact. Remember, tannins tend to help proteins settle out. So tannins can actually almost act like a fining agent in a way for proteins, and so enzymes are proteins. And so high tannin wines and meads, it doesn't last as long, but it might not have to last as long. You may use it at certain times, and then later on it may disappear. So you can use it right at the time of the press of the grapes or the fruit to delay the malolactic fermentation. You can remove it later with bentonite, which bentonite removes proteins, and then you can pitch your malolactic bacteria after that because the lysozyme is gone. And here's just a sort of a picture of how you might use it. You might pitch the lysozyme right at the beginning and sulfate to try to inhibit some of the wild bacteria, and you have your yeast going at the time. And then after alcoholic fermentation is done, you would pitch your selected strain of malolactic bacteria, and then you would pitch sulfites after that's done to prevent, to stabilize it, prevent oxidation, and also prevent any reactivation when it's bottled. Sterile filtration can be useful, not just for bacteria, of course, but to prevent any type of microbial activity in the bottle. You have to be have really good, aseptic technique. Even if just a few of them get in there, they can restart. And anybody who's ever had that happen. So it's still a good idea. And you don't want to do depth filtration. That's the other thing. So a lot of the filters that we get as homebrewers specifically, they're not sterile filters. They're not absolute filters. They're what we call nominal. So you have to use an absolute filter that can actually stop these, and that's through surface filtration. And that would be basically like a membrane filter. This is often used right before bottling. So you may do your filtration to clarify the mead, and then right before bottling, right before it goes into your bottling line. And again, I'm talking more about commercial meaderies and wineries, but there are some homebrewers I know that dabble with this. But for extra security, it's still wise to maintain adequate sulfite after the sterile filtration, just in case a couple of these little microbes got in there and snuck in somewhere that you didn't know about. So this is something really not available to us as mead makers, even commercial mead makers. It has some safety training, and it requires a specialized dosing machine, like $74,000. So, but this is what some of the big wineries might do to prevent it. Fumaric acid, I have never used this. I just am putting up here again as a knowledge, just to be aware there are some other techniques that are used by wineries to prevent MLF. So one of the other things too is if you're doing a malolactic fermentation and you want to move it to the next step, maybe you want to pull it out of the barrel, or maybe you want to, bottle it, you want to make sure that it's complete. Or if you want the malic acid to be fully converted, you can do some of that, by eyeballing it. Is it still cloudy? Is there CO2 forming? Or by taste, but it's not going to be quite as good as measuring it, to be sure. And so there's different ways to do that. A common way is paper chromatography. We do that. You can buy these through some of the homebrew suppliers. There's an enzymatic method, and then Vinmetrica actually has a CO2 biopressure signal method. So the way that paper chromatography works is you have these small samples of your mead or wine, and it's that you have these little standards of acid, tartaric, malic, and lactic acid, are put onto the paper along with the samples of wine and mead, and you put them in a jar with the butanol formic acid solvent and a green indicator. You leave it overnight, and as the solvent and indicator moves upwards, soaks up through the paper, over about 24 hours or so, and then it's dried, you can see where each acid is deposited and use that so that, and I have a picture here that makes a lot more sense than me trying to explain it. And by comparing the spots of the sample of mead / wine / Sizer to the spots where the actual tartaric acid, the malic acid, the lactic acid went, you can determine, is the malolactic fermentation complete, or is it partial, or has it not even started? And so this is a lot easier to explain. So the L's are the lactic acid, the T is the tartaric acid, and the M is the malolactic acid indicator. And so it was put into this, and these are multiple samples, each of them going up and down. And so these here are samples of mead where the malolactic fermentation is complete, because there's no spot lighting up where the malic acid is. These are ones that the malolactic fermentation has not started, because you have tartaric acid and malic acid lighting up. And then here is what it looks like if you have it's partial. So it's started, but it's not completed. Here's the Acuvin, and so it's a quick test. It doesn't, give you like, it gives you a general range of where it is, but if it's still, very purple, you're like, oh, it hasn't really happened. So you want it to be like minimal, so where there's like no color at all. The tests are a little bit costly. They're like, $3-4 per test. So if you're doing a lot of them and repeatedly, but it's maybe a little easier than some of the other methods. And then the Vinimetrica has this SC50. I don't have this. I tend to use the chromatography or the Acuvin, but it basically can convert the signal into for the SC300 that a lot of us have, and then you can use that to determine what the malolactic acid is. There's other methods. That's if you're a commercial winery, or some of them, these are would be like university level testing. These are not something that a home brewer is going to do, and probably not most commercial meaderies either. So to finish up on my talk, it can be very useful in not just wines and ciders, but meads that are like them. So Piements, Sizers, certain melomels. They can help lower acidity and tartness, but they can do a lot more than that. Microbial stability, so you don't have malolactic fermentation within the bottle. But I think the most valuable effect of the malolactic fermentation actually is not the acidity, or it's lowering the acidity, but it's actually the complexity that it gives. And it's hard to describe. It's hard to put into words. It just seems rounder, and it seems more complex as compared to one that I did not do a MLF, which is, it's crisp, it's acid, but it doesn't have some of that complexity that you get from doing a malolactic fermentation. Some of the malolactic bacteria can have unwanted effects, too much diacetyl or some of these other effects, but some of these might be more likely if you're using a spontaneous MLF. So that's why we tend to recommend using a selected strain, so that you're less likely to have surprises. And then try to optimize the fermentation with nutrient additions. And again, those are not absolutely necessary. You can pull it off without. We did it for many, many years without, but it does go faster using them. And try to avoid, unfavorable conditions, which mainly sulfites are the number one, too high of an alcohol. Bacteria, they like it relatively warm, but not hot. So, like room temperature, 64 to 72 degrees. And I've got all my references. Hopefully you guys can get a copy of, I'll have a PDF handout of this somewhere. So hopefully you guys can get a copy of, so you can have all these references also for yourself. So that's the end of my my presentation. But I'm certainly open to questions and things like that. I've been ignoring the chat because I've been, basically focusing on my presentation. So.
All right, great. Great job, Tom. That was tremendous, man. Would you like me to run off questions for you from the chat?
Sure, yeah.
All right, great. So let's see. Jolie is asking, is the CO2 production enough to carbonate with, or is it just carbonic acid?
Yeah, you're not going to really carbonate with it. it's not going to like blow corks out of the bottle. I mean, anything's possible, but it's more of a prickle. It's more of like a pétillance. It's not like a, it's not like a full blown carbonation that you would get if you had a yeast with sugar in that.
Let's see. Matthew Mead is asking, is there any way to identify a wild malolactic fermentation?
Yeah, if it happened without you putting anything in there. Pretty
point.
much. Yeah, if it already you're having something happening and you had not added a selected culture, then it's obviously a wild culture.
All right. Let's see. James Davis is asking, how do you test for malic levels?
I actually I played around with the paper chromatography because I'm kind of sciencey and it looks kind of cool having these paper things and then hanging them out and drying them. The Acuvin actually is good enough. I just need to know, is it still present, and so then I need to let that fermentation go longer, or is it pretty much absent? So that's pretty much what I do. I'd like to get the vinimetric attachment, but you can't have every toy that you'd like to have in your mead lab. I mean, I would like to have it, but yeah, no, I don't.
Let's see. Leaf Stevens asks, is there a commercial MLF culture you would recommend?
I've used different ones. I don't really have a favorite. I've played around. There's 4 or 5 different ones. Oh boy, I should have it. Let me see. I had it. Oh, I took it out of my presentation because I didn't have the samples that I was going to share with you. There's one VP 41 that I've had good success with. There's another one called Beta. And one of the things I found is, at least my experience, they're not as dramatically different as, say, between yeast strains. I find yeast strains that, the commercial yeast strains we use, they seem to be much more dramatically different, in their character as compared to the MLF strains, at least me using it in mead and wine. I mean, there are differences, but it's not like it's a dramatic that you can say, oh yeah, this is that malolactic bacteria strain. Definitely side by side, you can tell a difference, definitely for sure. But it's not like somebody's going to pour somebody I mean, maybe there's somebody that can say, oh, I know what bacteria you use. It's not, for me, it's not quite as dramatic.
All right, let's see. Joe Lee is asking, how does residual sugar and malolactic fermentation work?
So you're trying to have residual sugar and do a malolactic fermentation. If there is sugar present, the bacteria can work on that too. But if you want to make let's say you're trying to make a mead that has residual sugar, that's going to be hard to pull off because you're not really going to, you really should not be using sorbate because of the chance that the malolactic bacteria can wake up and work that. That said, I've actually played around with that just because I'm a sciencey guy, and not with a big batch, but just with smaller ones. I'm like, this is interesting. This had a malolactic fermentation, but maybe I want to have a little residual sugar. But if I add sorbate, what if the bacteria work on it? But the bacteria fermentation has already been done. And so what I have done in those situations is I hit it with high dose lysozyme, so that'll deactivate any bacteria that may still be present. And then I made sure my sulfite levels were high. So normally we try to have a molecular, SO2 of like 0.8. I made sure it was like 1.2 or 1.5. And then I drank them quick. So I didn't keep them around for a year. I drank them like in 3 months or 6 months. And it was okay. I didn't have the geranium happen in those times I tried that. But I don't really recommend it. I mean, if you want to do it as a home brewer to mess around, knowing that you might mess up a batch, or you might actually get geranium taintas, go for it. But that's not something that I normally would recommend.
All right, let's see. Leaf Stevens is asking, when you do malolactic fermentation in a barrel, do you leave any headspace?
Not too much. It doesn't foam. Yeah, so it doesn't foam like yeast does. You're not going to have a bunch of foam. So no, not really. You do want to have it so it can actually, blow off the CO2 it's forming. So you do want some kind of, airlock of some kind that's going to allow it to blow off. But they don't foam the way that yeast foams up. So, yeah, no, you don't really need to worry about headspace with them.
All right. Another question here is from John Herman. He says, what expectations can one have regarding secondary attenuation? He continues on here. Short of fermenting to dryness, can you know you have mitigated future fermentations based on attenuation level, or would you just wait for the malolactic fermentation to stall and call it good?
Yeah, that's a lot. That's basically what I do is I wait for it to stall. It's what I do, and there's many ways to do this. You can put the bacteria in at the same time as the yeast. Most of us don't, and so I basically let the yeast fermentation happen, and then when it's not completely clear, but most of the gross lees have settled out, so it's still a little hazy with the yeast. So I know there's going to be some fine lees happening. That's when I put it in the barrel, and I know that most of the sugar is out because I've measured it. It might not be completely bone dry, but the yeast is really not working much anymore. And that's when I put in the MLF bacteria, or if it's a barrel I already did the MLF in, the bacteria are already there. Most of the time you don't have to repitch. They're going to just be in that barrel for as long as you put stuff in it. And then it'll start working again. Now, let's say I did that and winter hits and I have it stored and it's kind of chilly. Maybe it might not happen until later. So if it's not much is happening, I might wait until the following, spring or early summer before I pull it out of that barrel because I want to get some oak into it anyway. But yeah, pretty much I'll let that happen, and then if I'm curious, I'll test for malic acid, and if the malic acid is gone, then I know it did its job. Sometimes a part uh, so I may pull it out of the barrel and then I sulfite it, and that's going to be enough to basically deal with whatever remaining bacteria might still be there.
All right, very cool. It looks like we got one more question from Matthew Mead. He's asking, is shutting down a wild malolactic fermentation as simple as adding sulfites?
Pretty much. Yeah, they're very sensitive to sulfites. I've had some, like I had a batch of mead that was sitting and I didn't intend to for anything to happen, and it was bone dry. And then I tasted it and there was like a little tingle of carbonation happening and a little tingle, a little haziness. And I'm like, I don't think that's a yeast. I think it's a bacteria. And I just I hit it with like 100 parts per million of sulfite, and that knocked the heck out of it, and it was gone. And actually, it wasn't really a well sulfited batch anyways where that'll happen in. So that 100 most of it's going to bind, and I'll retest the sulfites like a week later, and it might only be like 20, parts per million free SO2 in there. So yeah, I will hit it hard if there's a unwanted malolactic starting in some batch that maybe I cross contaminated because I didn't have good technique or whatever. I used the same wine thief in the same, two different batches. But yeah, adding sulfites should be enough to shut it down.
Very cool. And I've got one. I can't really think of an instance where this would probably even be realistically applicable, but it was just out of curiosity, because I know like a lot of strains of lactobacillus, at least, have like a very low tolerance to the IBUs and hops. Do you know by chance if any malolactic cultures would also have that kind of sensitivity, or?
I have no idea. I have no clue.
Yeah, I can't think of a situation where that would even come up, but like a big acidic standard strength wine mead with hops, I don't know, where you would need malolactic fermentation to soften it. I can't really see that happening, but
I have no idea. I do not know the answer to that.
Yeah, I was just curious, but and I guess one more here from Timothy Leber. He's asking, what about stopping it short for complexity?
I kind of mentioned that. Yeah, that's exactly. You don't have to do a complete malolactic fermentation, because maybe if you take all the malolactic acid and convert it to lactic acid, you're going to lose some of that crispness. Maybe, and where I could envision this, it would be like an extremely high malolactic, say like apples. You have a sizer and it's so acidic, but you don't want to remove all of it because then it's going to be kind of flat. You want some of that acid because apples are appley. I mean, they're high acid. So you could do a partial malolactic fermentation. And when you get it to where I like where this is, and it's not completed, but it's still tart enough, I've got a little complexity, but I don't want all the acid to be gone completely. You can just stop it at that point by adding sulfites or lysozyme if you want to, or both.
All right, very cool. Well, we don't have any more questions in the chat, and I can't think of any myself. But is there any final notes you kind of want to leave everybody with?
You know, it's a type of fermentation we don't really think about a lot as mead makers. You know, and I came to it as a winemaker, and I think there's a lot of opportunity for experimentation here. I mean, obviously in the Pymonts and the Sizers and those that have malic acid, but I'm still really curious about what is it going to do in you know, in meads that are not high in malic acid. Is it only going to be bad stuff like volatile acidity? But wait, we're using selected strains, and they shouldn't do that quite as much as a wild strain. I think there's a lot of opportunity to investigate. Is it going to do something good, or is it going to do something bad, or something, you know? And I've had mixed experience with it. Some of them have been okay, and some have been, and I'm talking about my okay, so really okay, and others have been, you know, not okay at all. And so I think there's some opportunity there to look at, you know, in mead in particular, because a lot of us, you know, we try to transfer our wine knowledge or our beer brewing knowledge to mead, and there's definitely a lot of crossover, obviously, but it's not a perfect crossover. So I think there's a lot of opportunity of learning and even a little bit of research on some of what some of these might do to mead.
Well, as always, and it's always expected of you, obviously, tremendous job putting this all together. There's a ton of information, and yeah, this recording from this talk, as well as all the others, will be available for everybody to pull off of the AMMA's website, including the speaker deck as well. Once the entire conference is over, we'll have everything up shortly after we finish the last presentation. So I'm sure everybody can't wait to get their hands on all that information that you passed on in the speaker deck.
Well, thank you.
All right. Well, as always, man, awesome job. Thanks again, Tom. Thanks again
Cheers.
to everybody for attending, and we'll see you all next week. All right. Thanks. Have a good night.